Look around you. Steel is everywhere, in the car you drive, the buildings you work in, the tools you use every day. But here's the thing most people don't know. Steel isn't just steel. A knife blade and a car door are made from fundamentally different materials at the microscopic level, even though they're both called steel. Today, we're diving deep into the 7 microstructure phases that make steel the most versatile material in engineering. By the end of this video, you'll understand exactly why some steels are soft and ductile, while others are incredibly hard and brittle. Let's get started. Here's the fundamental principle. Steel's properties are controlled by its microstructure, which is determined by 2 main factors: carbon content and heat treatment. Think of carbon as the seasoning in a recipe. Too little, and your steel is soft and easy to bend. Too much, and it becomes hard but brittle. But it's not just about how much carbon you add, it's about how you cool the steel after heating it. Cool it slowly, and you get one microstructure. Cool it rapidly by quenching in water or oil, and you get something completely different. This is where the magic happens. There are 7 primary microstructure phases you need to know. First, we have ferrite, the softest phase, found in low-carbon steels. Next is austenite, the high-temperature phase that only exists when steel is hot. Then there's cementite, an incredibly hard but brittle iron carbide. Pearlite is a beautiful layered structure that gives medium carbon steels their balanced properties. Bainite is the modern engineer's favorite, stronger than pearlite but tougher than martensite. Speaking of martensite, that's the hardest phase, achieved through rapid quenching. And finally, retained austenite, the unstable phase that sometimes sticks around at room temperature. Let's explore each one in detail. Let's start with ferrite. This is the softest phase in steel, and it has a body-centered cubic crystal structure, that's BCC for short. Ferrite can only hold up to 0.02% carbon, which is practically nothing. Under a microscope, ferrite appears as light-colored, uniform grains. It's stable below 727 degrees Celsius. Because it's so soft and ductile, ferrite is perfect for applications where you need to bend or form the steel. Think car body panels, sheet metal, or wire. Ferrite is also magnetic, which is why a magnet sticks to most low-carbon steels. If you're working with steel that's easy to cut, weld, and form, you're probably working with a ferrite-dominant microstructure. Next up is austenite, the high-temperature phase. Unlike ferrite, austenite has a face-centered cubic structure, FCC, which can hold much more carbon, up to 2.1%. Austenite only exists when steel is heated between 727 and 1495 degrees Celsius. At room temperature, you won't see austenite in regular carbon steel, it transforms to other phases as it cools. But here's the interesting part, austenite is non-magnetic, which is why hot steel doesn't stick to a magnet. This phase is crucial for heat treatment because it's the starting point for creating harder phases like martensite and bainite. Some special steels, like stainless steels with lots of nickel, can keep their austenite structure even at room temperature. That's why a stainless steel kitchen sink isn't magnetic. Cementite is where things get interesting. This phase is iron carbide, chemically written as Fa3C, and it contains 6.67% carbon. That's the maximum carbon that can exist in this compound. Cementite is extremely hard but also extremely brittle. You'll never see cementite by itself in useful steel, it always appears alongside other phases. Under a microscope, cementite shows up as white networks or layers. It's the cementite that gives pearlite and bainite their hardness. Think of cementite as the reinforcing bars in concrete, it's what makes the structure strong, but it needs to be properly distributed within softer phases to be useful. Now we come to pearlite, one of the most beautiful microstructures you'll see under a microscope. Pearlite gets its name because it has a mother-of-pearl-like appearance. It's not a single phase, it's a mixture of alternating layers of ferrite and cementite. These layers form when steel with about 0.8% carbon is cooled slowly from the austenite region, right around 727 degrees Celsius. Under magnification, you can see these alternating light and dark layers, like a fingerprint. Pearlite offers an excellent balance of strength and ductility, which is why it's common in medium carbon steels. You'll find pearlite in railroad rails, which need to be strong enough to support heavy loads but tough enough not to crack. The spacing between these layers determines the properties, finer spacing means higher strength. Bainite is the phase that modern metallurgists love. It forms when you cool steel at a controlled rate through temperatures between 250 and 550 degrees Celsius, faster than pearlite formation but slower than martensite. Under the microscope, Bainite has a distinctive feathery or needle-like appearance. It's composed of fine ferrite needles with tiny carbide particles distributed throughout. Here's why engineers love it. Bainite is stronger than pearlite but tougher than martensite. It gives you the best of both worlds. You'll find bainitic steels in high-strength automotive components, especially in modern advanced high-strength steels or AHSS. These steels make cars lighter and safer at the same time. Bainite is also popular in heavy machinery and gears where you need high strength without sacrificing toughness. Martensite is the rockstar of steel phasers. It's the hardest microstructure you can achieve through heat treatment. To create martensite, you heat steel into the austenite range and then quench it rapidly in water or oil. The cooling happens so fast that carbon atoms don't have time to diffuse out, they get trapped, distorting the crystal structure from cubic to body-centered tetragonal, or BCT. This distortion creates incredible hardness. Under a microscope, martensite appears as fine needles or laths. It's so hard it can cut through other metals, which is exactly why cutting tools, knife blades, and dies are made from martensitic steel. But here's the catch, martensite is extremely brittle in its quenched condition. Drop a fully hardened tool, and it might shatter. That's why martensitic steels are almost always tempered, reheated to reduce brittleness while keeping most of the hardness. Our final phase is retained austenite, the phase that wasn't supposed to be there. Remember how austenite normally only exists at high temperatures? Well, sometimes when you quench steel, especially high carbon or highly alloyed steel, some of the austenite doesn't transform. It gets retained at room temperature in a metastable state. This retained austenite appears as light, irregular regions under a microscope. Now, is this good or bad? It depends. In precision tools or gauges, retained austenite is a problem because it can transform over time, changing the dimensions. But in some modern steels, like trip steels, that's transformation-induced plasticity steels, retained austenite is actually beneficial. Under stress, it transforms to martensite, creating a strengthening effect. This makes the steel both strong and ductile, which is perfect for automotive crash structures. To understand how all these phases relate to each other, we need to look at the iron-carbon phase diagram. This might look complex, but it's actually a roadmap. The vertical axis is temperature, and the horizontal axis is carbon content. At high temperatures above 727 degrees Celsius, we're in the austenite region, shown here in yellow. When we cool down slowly, we cross this line at 727 degrees, called the eutectoid temperature. At this point, austenite transforms into ferrite and cementite, which together form pearlite. Notice how steel with 0.8% carbon transforms completely to pearlite. This is the eutectoid composition. Below 0.8% carbon, you get a mixture of ferrite and pearlite. Above 0.8%, you get cementite networks and pearlite. But, and this is important, this diagram only shows equilibrium cooling. In the real world, we don't always cool slowly. Cool faster, and you can form bainite in this intermediate region. Quench rapidly, and you skip these transformations entirely, creating martensite. This diagram is the foundation of heat treatment. So how do you get the microstructure you want? It all comes down to heat treatment. Let's summarize. If you want a soft, formable steel, you anneal it, heat it up and cool it slowly in the furnace. This gives you ferrite or coarse pearlite. Need something stronger with better toughness? Normalize it, heat it up and cool it in air. This produces fine pearlite or bainite depending on your steel composition. Want maximum hardness for a cutting tool? That's when you quench, heat it into the austenite range and plunge it into water or oil for rapid cooling. This creates martensite. But remember, you'll need to temper that martensite afterward to reduce brittleness. Different tempering temperatures give you different combinations of hardness and toughness. Low temperature tempering keeps it hard, high temperature tempering makes it tougher. The art of metallurgy is choosing the right combination for your application. Let's bring this all together with real-world examples. That knife in your kitchen? If it's a good chef's knife, it's probably made from martensite steel that's been quenched and tempered to around 58 to 62 Rockwell C. The blade needs to be hard enough to hold a sharp edge but not so brittle that it chips. The car you drive? The body panels are mostly ferritic steel, soft and formable so they can be stamped into complex shapes. But the structural crash members? Those are increasingly made from advanced high-strength steels with bainitic microstructures, giving maximum strength for passenger safety while keeping weight down. Railroad rails are made from pearlitic steel. They need to resist wear from millions of wheel passes but also resist cracking under impact loads. High-speed drill bits? Fully martensite, tempered just enough to prevent shattering. Every one of these applications requires a specific microstructure, engineered at the atomic level to do its job. Let's wrap this up with the key takeaways. First, steel is not just steel. Its properties are determined by microstructure at the atomic level. Second, carbon content is the primary variable. More carbon means more potential for hardness, but only if you heat treat it correctly. Third, cooling rate is everything. Slow cooling gives you soft phases like ferrite and pearlite. Controlled cooling gives you bainite. Rapid quenching gives you martensite. Fourth, each microstructure phase has specific properties. Ferrite is soft, pearlite is balanced, bainite is strong and tough, and martensite is the hardest. Fifth, heat treatment is how we engineer these microstructures. It's not magic, it's science. And finally, the right microstructure for the right application is what makes steel the most versatile material in engineering. Understanding these 7 phases gives you the power to select or specify the correct steel for any job. If you found this video helpful, make sure to hit that like button and subscribe to WeldFab World for more content on metallurgy, welding, and fabrication. In the comments below, let me know which microstructure phase you found most interesting, or if you have questions about heat treating specific steels. We've got more videos coming on advanced heat treatment techniques, steel selection for different applications, and deep dives into specialty steels. For downloadable resources, including a detailed PDF guide on steel microstructures and a reference chart you can print for your shop, check out the link in the description below. Don't forget to visit weldfabworld.com for articles, tutorials, and more technical content. Thanks for watching, and remember, understanding microstructure is the key to mastering steel. I'll see you in the next video.